Thank you. Thank you for the introduction, and thank you to the committee for this honor. So I'm going to talk about efficient verifiable delay functions. So first, what are verifiable delay functions? They are functions that are meant to slow things down when you need things not to go too fast. We usually want things to go as fast as possible, but sometimes slowing things down can be useful. So what are they? They were formalized last year by Bonnet, Bono, Boons, and Fish. A VDF, for short, for a verifiable delay function, is a function that requires time to evaluate. It means that it requires a sequential amount of operation, and you cannot take advantage of parallel power to spend less time computing. So you want it to require really sequential operations. But then, even though the evaluation takes time, you want the verification to be efficient. So the output, once known, can be efficiently verified to be the correct output by anyone. So syntactically, it's essentially three components. A setup procedure, which takes as input a time parameter t. You can imagine t to be 10 minutes. And will output some public parameters. Then you have an evaluation procedure, which takes an input x and gives some output y, and maybe together with a proof pi. This evaluation procedure is the procedure that is meant to take time t to evaluate. Then you have the verification procedure that takes x and y, and maybe the help of a proof pi, and will decide whether or not y is the correct output for the input x. So this is for the syntax, but the security requirements, we have two of them. They are the following. First, we need sequentiality. Sequentiality means that if A is a parallel algorithm that runs in time strictly less than t, then it will not be able to distinguish the correct output from a random value. So an algorithm that takes time less than t cannot learn anything about the output. If you really want to know anything about the output of the evaluation, you need to spend time t. So for those of you who attended the talks on proofs of sequential work yesterday, this looks a whole lot like a proof of sequential work, except we want one more property, which is the uniqueness of the output. We want that on input x, there is a unique correct output y. So if the verification passes for two pairs xy and xy prime, we must have that y equals y prime. This is the uniqueness, which means that the verifiable delay function is actually a function. So that's for the definition, but a little bit of motivation. What are they good for? The first application of VDFs was for generating public randomness. Public randomness is just randomness that is meant to be publicly available and can have an impact on a lot of people who care about it being uncorrupted, really random. So this is a problem that has motivated people for a while, for national lotteries, for sporting events, or tie-breaking in elections. So we've come up with a lot of ad hoc methods to generate public randomness involving complex machines, bolts flying around, or simply tossing a coin. But of course, if you want to use public randomness in a more technical setting, and it's indeed a very useful tool to have, for instance, in consensus protocols, then these ad hoc methods, of course, won't do. You want a cryptographic solution. There are very simple cryptographic solutions. Say you have a fixed group G of people who want to agree on some randomness. What they can do is each of these people generate their own privately a random bit string RA, and then they will broadcast a commitment on this random string. So the commitment, it's a cryptographic commitment that is hiding and binding. And so they broadcast this commitment, and once all the commitments have been received by everyone, you open the commitments, so you broadcast all the values RA, and the randomness at the end of the protocol will be the XOR of all these random bit strings. And one can show that if the commitment is really hiding and binding, then the random output you get at the end is truly secure, is good randomness as long as at least one of the participants was honest. This is the commits then reveal protocol. The problem with this protocol is that it does not scale. We assume that we have a fixed set of participants G, and all the participants to the protocol must be there at the beginning and must stay until the end. If someone drops in the middle, meaning that someone committed a random value here but is not here for the second round of opening the commitments, then you have to start all over again. This is really not good. The solution to this problem was proposed a few years ago through a protocol called Unicorn for uncontestable random number. And the basic idea is to make it much simpler. You don't have commitments. the parties directly reveal their random bit strings are A. OK, so much simpler, no commitments, so no opening phase. People cannot leave in the middle because there's only one round. They just throw their randomness. But of course, this is trouble, because the last person to reveal now has full control of the output. If I know all the random strings of everyone, and I just have to decide my own at the end, I can fully determine the output R by choosing the correct random string. We can prevent this by, instead of using the XOR of all the values, concatenating all these random strings and feeding them to a function f that takes time to evaluate. If this function takes time 10 minutes to evaluate, then the output of the protocol will not be known, so the random value will not be known until 10 minutes after the last random value is revealed. Therefore, one cannot do any meaningful decision at the moment they have to reveal their random value, because they don't know what the output will be yet. It's going to be determined only 10 minutes later. So this function f was called a SLOTH in this work for a slow-timed hash function. And essentially, the properties you want is that it takes time to evaluate, for instance, 10 minutes, but you also want it to be easy to verify, so that anyone can easily verify that the protocol went correctly and that the output that is claimed is the correct output. And this sloth hash function had the slowness property, and it was easier to verify than to evaluate, but only by a constant factor. So if it was taking 10 minutes to evaluate, it would take maybe 1,000 times less time to verify, but you could not do much better than that. But instead, we can use a verifiable delay function. So now that we know what they can be useful for, how do we construct one? So a verifiable delay function is a function that is designed to be slow. How can we do this? We want a sequential amount of computation that cannot be parallelized. So maybe we can just try iterated hashing. We have an input x, we hash it. We hash the output of this hash function, we hash it again, as many times as you need until the required time reaches this bound t that you want. OK, and then the output would be the iterated hash, this value y here. So this is indeed slow and sequential, but it's not really easy to check that the output is correct, right? How do you check efficiently that f of x equals y? There's no simple and efficient way. You could come up with some ways, maybe using snarks to make the verification simpler than actually recomputing everything, but that wouldn't be simple and efficient. Instead of hashing, you could try to use some structures with more algebra involved and try to make things more efficient. So we can draw inspiration from time lock puzzles. The idea here is to fix a group G of unknown order. A group of unknown order, think about an RSA group, for instance, Z mod NZ, where n is a Z mod NZ star, where n is a product of two large prime numbers. If you don't know the factorization, then you don't know the order of the group. Now, you're given an element x in this group, and if you want to compute x to the power 2 to the power t, you can do it by squaring it t times sequentially. So you take x, you square it, you square the result, you do this t times, and you get at the end x to the power 2 to the power t. And if you knew the order of the group, you could take 2 to the power t, reduce it modulo the order of the group, and obtain the final result as just one small exponentiation. But if you don't know the order of the group, it seems you have no choice but to compute the t squarings one after the other, and there is no shortcut. So now the VDF could simply be f of x equals x to the power 2 to the power t. And that seems sequential, but is it really easier to verify? Well, this is the approach that was also taken in a concurrent work by Pietschak. So really, the construction is having the VDF be x to the power 2 to the power t, and then coming up with some way to prove that the result is correct without requiring the verifier to do the full computation by himself. So here's the new problem we're trying to solve. We're given a group of unknown order. Alice claims that some elements x and y satisfy y equals x to the power 2 to the power t. And Alice tries to convince Bob, or actually the rest of the world, but let's start with just Bob, that this equality holds, without forcing Bob to actually redo the computation by himself. So remember that in a VDF, you not only have the output y, but you are also allowed to output a little proof pi that will be a helper for the verification. So Alice is going to compute x to the power 2 to the power t together with a proof pi, and the triple xy pi will be used to verify that the relation holds. I'm going to present the method as an interactive protocol where Alice is interacting with Bob, trying to convince him, and then you can turn this interactive protocol into a non-interactive proof by some standard Fiat-Shamir transform. So here's the protocol. You start with x and y, and Alice tries to prove that y is x to the power 2 to the power t. Bob challenges Alice. He chooses a random large prime number L, large, think a prime number of 200 bits, and sends it to Alice. Now Alice computes the Euclidean division of 2 to the power t by this prime L. So 2 to the power t is the quotient q multiplied by L plus the remainder r. And the proof that she's sending to Bob is x to the power q. OK. Now Bob can easily recover the remainder, it's 2 to the power t modulo L, and he's going to check that pi to the power L times x to the power r is y. So it's very easy to verify that everything is going as expected, then the equality should hold. Pi to the power L, it's just x to the power q times L, multiplied by x to the r, we get on this side x to the power q L plus r, so x to the power 2 to the t. So this equality should really be x to the power 2 to the t equals y. OK. So the non-interactive version of this protocol is very straightforward. Instead of having Bob generate L, you just take L to be the next prime of some hash of the input of the protocol. Before going into why this should be secure, here's a little comparison with some previous and concurrent work. So if we look first at the SLOTH hash function, the first one that I mentioned, the problem with the SLOTH hash function is that, so it's very good. The size of the proof is very small. It's just an element in a group. But the evaluation, the verification is not much faster than the evaluation. Here, t is the target time. These numbers should be taken a bit with a grain of salt because I'm expressing it asymptotically only as a function of the time, but not as a function of the security level. If you think about it 2 minutes, you can see that it's a problem because at some point the security becomes more important than the target time. If t becomes bigger than the time it takes to factor integers, then you're running into trouble. But these numbers give a good picture of what's happening in practice. OK. So the problem with the SLOTH hash function is this verification that is still linear in the required evaluation time. The Pietschak construction gives a huge improvement on the verifier, which requires only logarithmic time in the target evaluation time, at the cost of having a bit larger proofs, so log t elements in the group, and also at the cost of a little bit of overhead in the evaluation. So the evaluation should take time t, right? And this is 1 times t here. But then you have to compute the proof, and the proof will take a little bit of time. So this is negligible next to t, so it's fine. Now, in the work I'm presenting, the size of the proof is back to 1, very small, and the verifier has a constant amount of work to do to verify the correctness. And so you also have an overhead in the evaluation due to computing the proof. This overhead is a bit more important than the one in Pietschak. OK. So why should the construction be secure? Suppose that Alice is dishonest, meaning that she's trying to prove that y is equal to x to the power 2 to the power t, but it's actually not. So we can define this quantity w, which is the ratio of the two values. And when Alice is dishonest, this value is different from 1. And I claim that for Alice to be able to convince Bob successfully, she must be able to extract Lth root of this element w with good probability. This element w is fixed before Alice knows L. So Alice is supposed to find this element w, to find an element w in the group, of which she's going to be able to extract Lth root for random L. So why is that? If we look at the protocol, w is fixed at the initialization of the protocol. It depends only on the input of the protocol. Then Bob generates a random value L, and Alice computes a proof pi that passes the verification condition. So pi to the L times x to the r is y. Now, if we look at this ratio rho, which is pi divided by x to the q, and we do a little computation, we find that rho to the power L is W. In other words, rho is an Lth root of W. And that is supposed to be hard. This is what we call the adaptive root assumption. It's a game that's supposed to be hard in a group of unknown order. The adaptive root assumption holds in a group G if the following game is difficult. The player outputs an element W, which is not the neutral element of the group. Then the challenger generates a random prime number L. And then the player has to find an Lth root of W. So W to the power 1 over L. The question now is, in which groups does this assumption hold? The quick answer is in groups of unknown order. The more detailed answer is, well, we can construct some of them from number theory, and we have to take care a bit about possibly known subgroups and things like this. So I'm going to say a few words about that. We know already in cryptography how to generate groups of unknown order. I already mentioned the RSA group. So you can generate a number n, which is a product of two large primes p and q. And without knowing the factorization of n, the group z mod n z star has a known order. But it has a known subgroup of small order. So we have to be careful here. We know this subgroup plus or minus 1, and this can cause trouble. In the adaptive root assumption, I could say W equals minus 1. It's not the neutral element, but then I'm able to extract Lth root of minus 1 for arbitrary L. So what you want to do, in fact, is work in the RSA group quotiented by plus or minus 1. There's a problem in this setup, which is that you have to generate a group of unknown order, but unknown by anyone in the world. So you have to generate a number n that is a product of two large primes, and no one has to know the factorization. So there's solutions to that. You could assume some trusted setup. So if someone you trust, just have him generate your random RSA modulus. But of course, you don't want to do that. Another solution would be to generate a random very large n with a probabilistic guarantee that it must have large factors, but this won't be very efficient. Another solution is to run a big multi-party computation among a lot of people who will together generate an RSA modulus with the guarantee that if at least one of them is honest, then no one can recover the factorization. This is another possibility. A much more satisfying construction would be to use class groups, because it's very easy to generate class groups of which no one knows the factorization. You just have to generate a random large prime p. This prime doesn't have to be secret, so it's very easy to do. Then the imaginary quadratic field of discriminant minus p has a finite group associated to it called its class group, which I write G here. And computing the order of this class group is a difficult problem. The best known algorithms today have complexity LP of 1/2, so it's a larger complexity even than factoring. The big advantage of this setup is that it's very easy, very simple. You can even change p every time you evaluate your VDF. OK, now I need to say a few words about the problem of slowness in the real world. We are very carefully designing these functions to be slow. We want them to take 10 minutes and no less. But then you throw this in the real world, and engineers come in with new solutions that you didn't imagine to go much faster than expected. So the basic assumption is the time lock assumption. We say that given x in our group, computing x to the power 2 to the power t will require t sequential squarings. In other words, the required time is t times the latency of doing one squaring in the group. Now we need to understand exactly what is this latency. How fast can we do a squaring in the group? And more precisely, can a rich adversary get a much better latency than the easily available hardware? So the best way to test this assumption that someone very rich cannot do better is to throw a lot of money at it and see what people can do with it. And the best way to have a lot of money thrown at your problem is to get blockchain people interested. And this is what's happening. So Chia, starting with Chia, the Chia network is organizing a VDF competition whose goal is to implement the fastest possible class group arithmetic. They are currently running the second round with a total prize money of $100,000. And you can find more information at this web page. Then there is the Ethereum Foundation and Protocol Labs, who are running also a big competition, but this time not in the class group setup, but in the RSA setup. They want the fastest possible implementation of modular arithmetic, modulo a 2,000-bit RSA modulus. It's going to be 2 rounds. The first round is going to start this year. It's an FPGA competition of implementation of the arithmetic for a prize of $100,000. And next year is going to be an ASIC competition for a prize of $1 million. And they are targeting, I think, something like a latency of 1 nanosecond per squaring. And you can find more information there. Thank you for your attention.
So we have time for questions. Yeah, if you have a question, just walk to the microphone. You can also come here and get my microphone. Yeah, yeah.
Can you go back to slide 23?
Can I? What?
Go back to slide 23.
23. Yeah.
So for this assumption, you mean exactly time t times the latency of 1 squaring?
For this assumption,
You're assuming that computing t squarings is time exactly t times the latency of 1
yes.
squaring? Isn't this violated by known parallel algorithms for exponentiation? For instance, the Bernstein-Sorensen algorithm.
As far as I know, the best circuit implementations cannot take advantage of that. And the best way to go as fast as possible is to reduce the latency of a single squaring. Or maybe exponentiation by 4 can give some advantage. But beyond that, I think it's not known to be feasible.
You sure it isn't more like t divided by the log of the amount of hardware that the attacker spends, so the latency can keep going down and down and down depending on the amount of hardware?
I don't know. So the time lock assumption was kind of tested during the last 20 years by the time lock challenge. That was a challenge of this form, trying to compute x to the power 2 to the power t for a huge t as fast as possible. It was supposed to take 30 years. And in the end, it took something like 20 years. It was finished a few months ago. But the techniques that were used to do this computation were really t-sequential squarings and did not break this assumption.
All right, thanks.
Yeah. But I guess if you can get some faster parallel exponentiation. Well, there is $1 million. Well, if you can, so the competition is about implementing your exponentiation as fast as possible. So if you can do it by other means than reducing the latency, you still win.
Yeah, if you have a question, go ahead.
Yes. Do I understand correctly that to implement this thing or like do this thing, you either need a random oracle or interaction? For the protocol? Yes, or like in general for these verifiable delay functions. Yeah. We need what? Do we need like either interaction or random oracles? Yes. So we cannot do without them. We cannot do? Without we need one of those. So we cannot do without those. So not this construction indeed, because either you're going to have an interaction or you do the Fiat-Chain transform. But I don't know about the latest VDF proposals. There is one based on isogenies, I think, is not using a random oracle, but I'm not sure about that. Thank you.
Hey, might be a simple question, but so you have these properties that you need time t to recover this unique value y. Do you have under the same assumptions the property that y looks pseudo-random from the viewpoint of any adversary whose running time is bounded by t? Like, can I take an adversary that will run in time, say, strictly less than t, and giving either a y or a uniformly random value, and then assume that you will be unable to distinguish between the two?
Yeah, in limited time.
Okay. So then you can directly get some kind of delay encryption out of that by just, oh no, yeah, not directly. Okay, thank you.
Yeah, so the assumption is you're given the input, and you give and a random value, and no. You're given the output and a random value, and the adversary is only allowed to compute during time strictly less than t, and he has to distinguish which one is correct.
Okay. Thank you.
I have a question related to the class group construction you proposed. You said that calculating the unknown order requires L-half, which is harder than factoring. But are you talking about worst case? Are you talking about average case? Even the average case is not going to be enough, because for 1% of the cases, there could be a very easy algorithm for calculating the group order. So what exactly is known about the difficulty of solving the problem for a tiny fraction of cases?
So as far as I know, it's difficult for all class groups. So depending on, so which slide is it? Depending on the congruence of P mod 4, you're going to be able to determine if the class group have a small order of degree of order, a small subgroup of order 2, and that's pretty much all you're going to be able to do efficiently. And then I don't think there is any algorithm that would be faster than L of 1/2 for a carefully cooked P.
Regardless of how small the set of P's is.
Regardless of how small?
How small the set of P's.
Well, you're going to want to have P large enough, right?
Okay, so thanks.
Okay, I think we have grilled him now enough, and he deserves the prize twice. So let's thank him again.